So for these examples, we'll use some ideas that come from Pre-Calculus 1 and Pre-Calculus 2. And I'll link review videos below because I'll go a little quickly through these in order to evaluate the actual limit. But if you need to do more of a deep dive into reviewing these concepts, you can take a look at those videos below. So what we'll focus on too is also how I know that this is the route that we need to go with it. So again, with these limits, first thing we can do is try direct substitution. So we're evaluating the limit as h approaches 0 here. So I would go square root of 1 plus 0 minus 1 over 0. That's turning into a 0 over 0, which is undefined. So we don't want that. So what I want to know is, looking at this function, what can I do in order to simplify it? And something that I'm really focusing on here is the numerator. What I can see is that I have a radical involved and I have a two-term expression. So I have a radical plus or minus something else. And with that, a tool that we can use for simplifying is multiplying by conjugates. So what I'm focused on here is I see my square root symbol. I also see that I have subtraction with a second term in that numerator. So we have our numerator. What I would do is to multiply by the conjugate is, when we multiply, we have to multiply the numerator and denominator by the same thing because we're just simplifying. We don't want to actually change our function. So we're multiplying by a version of 1. And to make it a conjugate, what I would do is I would keep the terms the same. I would have 1 plus h. I'd have 1. But instead of subtraction between the two terms, I would have addition. And whatever I put in the numerator, I also have to put in the denominator. So in this case, we would be multiplying by a square root of 1 plus h with plus 1 on the outside. Notice I really didn't focus on that denominator at all. Having h down there, it's important, but it's not affecting how I create the conjugate. With that, I'm purely focused on the expression where I have the square root plus or minus something else. So why we do this is because then up in that numerator, we're going to FOIL. So we'll multiply the first terms, last, middle, and last. And so when we do that, what ends up happening is essentially using a difference of squares. So let me go ahead and write my next step here. So we're still evaluating the limit as h approaches 0. And what we'll have is a square root of 1 plus h times a square root of 1 plus h. So I'm going to go ahead and write this out. Square root of 1 plus h times square root of 1 plus h. And then we'll have a plus square root of 1 plus h, but then a minus square root of 1 plus h. So that's where it's so important to have opposite signs here, because we need that middle term to just turn into 0. So we have 0 coming through, and then I'll have a minus 1 times positive 1, which is just a minus 1. So really how this connects to our difference of squares is that if we see we have two terms, one's the addition of the two, one's the subtraction, when we multiply those, we'll have the square of the first term minus the square of the second term. In our denominator, we're just multiplying things, and my recommendation is to keep that factored as long as possible, because what we want to get to is some simplifying, and to simplify we need everything nice and factored. So with that, let's start simplifying the numerator. So carrying out those squares, we'd have a 1 plus h without a square root anymore because it got squared, and then minus 1 squared, which is just 1, and then the denominator h times 1 plus h plus 1. So in the numerator, all we're going to have left over is an h over h times square root 1 plus h plus 1. And now this is why we wanted to keep things factored in that denominator, because now you can see those h's cancel out, leaving me with a 1 in the numerator there. And notice throughout this, we want to keep that limit notation. We're still evaluating the limit as h approaches 0, but now in this next step, I can drop that limit notation because I'm plugging in h equals 0. So I'd have 1 over square root of 1 plus 0 plus 1, which is a 1/2. Now, with this, when we get to the end, we've simplified it. If you want to check your solutions at home, a good method would be graphing our function. So what we could do is graph the original function. So if I have f of x is equal to square root of 1 plus x minus 1 over x, if I try to get to that point where x is equal to 0, it's going to be undefined. But what I could see visually is that we are approaching a 1/2 right there. So that matches up with what we found algebraically. So you can get kind of a visual confirmation that things are lining up there. All right, so, oh, I'm sorry, I wrote rational functions there right at the top. It should be radical. I mean, it is rational as well, but really it's the radical piece, seeing that square root, that leads to using a conjugate. Okay, next up, working with trig functions. So again, let's go ahead and try to plug in pi over 2. So that would be a sine of 2 times pi over 2, which is just pi, and then cosine of pi over 2. Now what you should be comfortable with is making these substitutions without a calculator. So these are kind of our nice angles. So with that, I just want to think of the unit circle. So sine of pi would be over here, and it would be, if we're looking at -1, 0, it would be equivalent to the y coordinate. And then cosine of pi over 2 would be up here at 0, +1, and cosine uses the x coordinate. So this is giving us a 0 over 0, which is not going to work for us. So something we can use in simplifying are the identities, and if you don't have these memorized, that's okay. When we get to certain ones, there are ones that are good to have kind of ready to go, but for double angle, if we need to use it for anything, I would provide that identity for you if you need it. So this is going to use the double angle identity, where the angle is being multiplied by 2. So with that, we can look up that identity, get what the substitution looks like. So limit as t approaches pi over 2, that stays there. But now instead of sine of 2t, we can rewrite that as 2 times sine of t times cosine of t with that double angle replacement. And then we'll have cosine of t in the denominator. And then with that, we can cancel out those cosines so that really I'm just evaluating the limit as t approaches pi over 2 of 2 times sine of t. And now we can go ahead and make our substitution. So it's 2 times sine of pi over 2. Again, if I go back to my little sketch of the unit circle, that would be that coordinate 0, 1, and we're grabbing the y coordinate. So this would be 2 times 1, which is equal to 2. And then we could do is graph that original function and make sure that that's what we're seeing. All right. Last example here is going to use logarithm properties to help us simplify. So at this point, if we plug in, it's that we're taking natural log of 1 all over the place, and natural log of 1 is equal to 0. So we'd be getting a 0 in the numerator, 0 in the denominator. So what we're going to do is use logarithm properties, and there are quite a few that we're actually going to use in this scenario. We're kind of going to go back and forth a little bit too. So in the numerator, what we're seeing here is we have addition of 2 terms, and the key is that we're adding 2 logarithms that have the same base. So we have 2 natural logarithms that we're adding here. So with that, the property that we're using, if we're separated by addition, we could then combine those into a single logarithm and multiply the insides. So this would be x times x cubed, which would be x to the 4th, over, actually, okay, I'm going to go a little bit of the long route here, but it's more to make a point about the logarithm property, and then we'll undo it. But if you have a number on the outside of a logarithm, like we have 6 here, so 6 times natural log of x squared, that number comes inside as an exponent. So what we'll have is a natural logarithm of x squared then raised to the 6th power. So our exponent properties say when we have a power to a power, we multiply them together. So this would be x to the 12th. Okay. Next step. We can't cancel things yet. What we have inside those parentheses can't cancel with each other because they're stuck inside the logarithm. So instead we actually want to do the reverse of that property I just did in that denominator there, where we brought the number inside as an exponent. What we could do is go in reverse and bring that number out front as a multiplier. So we're going to do that in the numerator and denominator. So this would be the same thing as evaluating the limit as x approaches 1 of 4 times natural log of x over 12 times natural log of x. And now we can make cancellations. And actually everything with x wipes out. We just have a constant here. So there's nowhere to plug in 1, which is completely fine. All we'll have left over is 4/12, which is the equivalent of 1/3 for our final answer. Okay, so review of some different properties with different types of functions, and again, review as you need to in order to get those pre-calculus ideas solid. But with taking the limits, a key thing that happens here is make sure you hold on to that notation until you actually plug in the value in order to evaluate and get to a number at the end.